So how many of you here are on a team? Almost everybody? Sports, math, science, the race car team, Amnesty International, yeah? So how many of you have a robot on your team? That's a lot of people. That's really impressive. This is probably the right audience for this. So why do we have a robot on our team?
Because the purpose of the team is to use the robot.
That is correct. Anybody else? Why, maybe in 10 years, why would we want a robot on our team?
Optimize our team performance.
Optimize team performance. That's exactly right. Do you have another one?
They can go places humans can't go.
That's right, yeah. Access to areas. Here.
They're better than the other humans.
Better than humans. So that is true. Robots are very good at some things, and humans are very good at some other things. I'll let Professor Shah talk about exactly where the differences lie. Anybody else?
Performing menial tasks.
Performing menial tasks, the stuff you don't want to do. That's right. Anybody? Anybody else? Okay, last one.
Yeah, you can be more specialized in what you do.
More specialized, yeah. So there's a few questions in here. One is, how do we actually make the robot part of our team, right? You have to use it in this case, but how do we actually make it part of the team, and what are the mechanics for making that happen? And there's another question is, what is a good teammate? How do you actually quantify being good, right? And then, so those are both really hard problems, and those are both problems that Professor Shah is working on. And she has a very long list of accolades. I presume you guys have the book and you can read them. I think the one that hopefully resonates with all of you the most is she's on the list, the worldwide list of top 35 innovators under 35, or maybe just top innovators under 35. But it's super impressive and very, very much a distinguished honor to be on that list. And I hope you really enjoy what she has to say. So without further ado, Professor Shah.
Thank you so much. Thank you. All right, it is a pleasure to be here today. I'm so happy I have the microphone because I have a little bit of a cold, so please bear with me if I sniffle and cough in front of you today. So I'm Julie Shah. I lead the Interactive Robotics Lab here at MIT, which is a part of the Computer Science and Artificial Intelligence Laboratory. Have you guys spent time in Stata yet? Who's spent time in Stata? You haven't been through Stata yet? Well, I'm sure you will before the end of the program. It's the weird, robot-looking building. Do you know what I'm talking about? Is that a good description of it? Yeah. And I'm also faculty in the Aeroastro department here. And so what I'm going to talk about today is, well, how close are we to the perfect robot teammate? So this is the vision of my lab. We're trying to develop robots that we can work with as easily and naturally as we work with other people. So, teamwork is a really magical thing. I give a sports example to start, but everybody has their own sort of sport or their own team that they truly love. But I think everybody in the room has the indexed in their mind those few moments where there's this extraordinary play. For these few moments in time, everybody on that field or court or whatever, they just seemed to share a brain, and you just sat there and you were like, how did that happen? Who's had that experience? It's magical, right? How are we going to enable a robot to do that with us? Well, the interesting thing is it's magical, but it's actually something that we rely on more than in our teams, in our sports teams. So, for example, in operating rooms, this is an incredible example of truly outstanding teamwork. So if you've ever seen videos, even on TV, that kind of do this because it's real to life, the surgeon will put out his or her hand, and it's actually captured in this picture here. The surgeon will put out his or her hand, and the surgical assistant just puts the right instrument there without a word being exchanged, without the surgeon even looking to confirm that that's the right instrument for what they need. That's magic. So what is it that makes for effective teamwork? What are the characteristics that enable this? Well, to be a good team member, you need three things. You need to know what your partner is thinking. You need to be able to anticipate what they're going to do next. And then to work together, you need to be able to respond on the fly to disturbances that arise. So the vision in our lab is to try to enable a robot to do these three things. And we have sort of 3 lines of work in the lab focused on designing models and algorithms, artificial intelligence, that makes robots smart enough to work with us in this way. Okay, so how do we realize a robot teammate? How do we enable a robot to infer what we're thinking, what a human is thinking, anticipate what a human is going to do next, and then make quick adjustments when working with us? This is not an easy task because humans, like us, I'm not an alien, all of us, people, are like the ultimate like uncontrollable entity. You can't, like, who knows what a person is going to do next, right? But society works because we have some way to project or predict. So what does this require? Realizing a robot teammate requires, in sort of technical challenges, that we do 3 things. We need some way of being able to formalize the machine's representation of human mental state. And we need to think about, what are the mental states or the cognitive states that we need to formalize that will help that robot work with us effectively in teams? Even that is an open question, and it draws heavily from work in cognitive science and behavioral psychology. When we talk about teams, a key part of working effectively in a team is the ability to sort of infer all the implicit things, all the things that are unsaid. Like a medical student shadowing a doctor in a hospital is sort of implicitly learning the workflow of that hospital. When rooms get changed over, when a patient is transferred from one room to another. So somehow, we need to develop the right representations for all these implicit factors, preferences, constraints, and priorities that make teamwork possible. Representing these quantities, sort of formalizing what's in our brain, is the first step. But once we've formalized it, we need to develop models and algorithms that will allow a robot to infer these quantities and qualities. And this is not easy because one of the things that makes the human mind so special is our ability to process very complex information very efficiently. Existing machine learning techniques like big data, like deep learning, they require extraordinary amounts of data. But a medical student can shadow a doctor for a few days and really kind of like get a sense of what their role is in that team and how to do their job. So what we do in the lab is we look at how we can draw insight from well-established cognitive models to get some insight about how do people do this type of learning, do this type of inference efficiently, and then how do we design an AI or a robot system that can do it efficiently as well. And the last area is, well, if we have a robot that can learn the game, learn the implicit priorities, constraints, and preferences for working with us, it then needs to play the game. And to play the game, it can't just follow a fixed sequence of actions, right? It needs to be able to adjust. And so we work, I won't talk about it today, but we work on techniques for dynamic scheduling and dynamic plan execution that allow robots to reason on very sort of low-level granularity of timing of actions and make very fast adjustments based on what their human partner is doing. OK, so today what I'm going to do is talk about our progress, sort of where we are so far in developing a robot that can formalize humans' representations of cognitive state and that can infer those qualities and quantities, and look at, can that be useful? How does that help a robot to work with us? What is the state of the art today? And then I'll end the talk going through what I think are sort of the problem is not solved. I've been working on this problem for maybe 6 years on the faculty, and then maybe like 4 years on PhD before that, so that's 10 years. I have not entirely solved the perfect robot teammate, just as a spoiler. But we've made progress, and I'm going to talk about what are the open challenges that maybe some of you all can help us pursue in the coming decade. OK, so first, how do we think about formalizing human cognitive state for teams? Well, it is an open question. What are the states that need to be formalized? In our work, we started with 3, and then looked to see how far we can get with those 3. So what's a foundation of working effectively in a team? Well, you kind of need everybody to be on the same page. So can we formalize this idea of team consensus? And can we enable a robot to infer, based on our team planning conversation, whether we're on the same page, whether we have strong shared understanding with regard to what we're going to do together? And if we do, well, then the next thing we need to be able to infer is implicitly, either through conversation or observation, who's going to do what, in what order, how do we need to synchronize our actions? So that's like the team discussing their game plan before the game. We need to be able to listen to that conversation. The robot needs to be able to listen to that conversation and extract the team's plan so it knows its role in the team. And finally, we need to be able to learn policies that, ideally through observation of human decision making, learn policies that enable the robot to predict the decision a human is likely to make next or the action that they're likely to take. Okay, so, and I contend that if we can do these 3 things, we can enable new types of human-robot partnerships. Okay, so how do we do this? So we have these ideas, consensus, some plan that we've agreed to, some policy that predicts human behavior. How do we formalize these, and how do we infer them? So say these are, at a high level, the mental states of our human partner that we want to infer. Let's start with the first, or the first 2, and think about team consensus and team commitments. And think about like one of your team planning meetings, or an emergency response team's planning meeting when they're planning a deployment. You're going to sit around a table, and you're going to discuss who's going to do what and in what order. You're going to parse out tasks. Now, okay, so who's recently been in a meeting like that? Are you guys all doing team projects? How do you guys work together if you're not in team meetings? No, really, I want to know. Is it like all like online now? So who's recently been in a meeting or in a setting like that? Maybe not like a formal meeting where you called the meeting at 2 o'clock. Okay, that makes a little more sense. Good. Okay. I don't know. Who knows? Who knows? Forms of teaming are constantly changing. Okay. So now think of that last meeting that you were in. Imagine yourself as a fly on the wall, and just like replay the conversation in your mind. Okay. What did that conversation look like? Like who said what? What were you pointing at? Were you looking at the computer? Whatever else. Okay. And think about what you can directly observe from what happened in that team meeting. Can you tell me from what you can directly observe how a machine can infer whether you all left that meeting on the same page with strong agreement on what you are all going to do? Like, how do you make the link from what a machine observes to that latent mental state? Does anybody have any ideas? Oh, go for it. Yeah.
Just analyzing the human expression, like facial expressions, like the weird emotional state.
Okay. So a hypothesis that emotional state might play a role in it, okay, which means we need to go from something related to the low-level features of your face to something related to emotion or affect, and then from there we need to somehow link it to consensus. Okay, reasonable. Other ideas? Yep.
Around the same amount, then that kind of means there's more of a discussion instead of like one person kind of leading and everybody else just going with it, whether they agree with it or not. So
Yeah.
a good discussion.
Nice, good. So we have this idea of multimodal data. We have this idea of information exchange potentially being important. Okay, one more idea. I'm going to take someone from the wings. Yeah, go for it.
I was just going to say, if everyone verbally commits to the project without like objections, then generally means that BWSI can agree.
Awesome. So all of you guys are sort of like, these are all like actual ideas that are documented in the cognitive science literature. Interestingly, multimodal data appears to play a smaller role than patterns in information exchange. And so what we did in the lab was work with this literature from cognitive science that tells us, what is it about how we come together, have a discussion, exchange information? What is it about those patterns of information exchange that can help us delineate whether a team has strong or weak shared understanding? And I'll come back to the sort of multimodal input in just a little bit. So we looked at that as well. So now, what's interesting is that a lot of this literature is qualitative. So extraordinarily rigorous work, but qualitative. And so seminal work by Barbara Eugenio, about 2000, in studying the human agreement process, what she posed was that the patterns in information exchange are crucial to delineating a team's shared understanding. So like at a high level, like the idea is if you spend your whole meeting just asking each other questions and then you like break and go home, like you're much less likely to all write down the same thing as to what you agreed to. But if you instead lay out all your information, fully deliberate on it, make proposals, accept those proposals, confirm those proposals, then you're going to be much more likely to write down the same things at the end of that meeting. Okay, so what Eugenio did beyond that was say, it's not just the individual dialogue acts, like if I ask a question or you answer that question, or I make a proposal and you accept the proposal, that matters. So it's not just sort of the, although balance of information exchange is actually known to be an incredibly important predictor of team performance, just so you guys know. The more you sort of balance speaking in a group, the better a team typically performs. That's a little different than inferring consensus. So inferring consensus, what Eugenio said was that it's not the individual dialogue acts that are meaningful, it's higher level patterns in these dialogue acts. And what she did was propose 4 of what she called dialogue features, which are basically like hand-generated patterns of these lower level dialogue acts, and was able to show that this would help you delineate strong and weak consensus in a team. So what we did was we sort of drew insight from the fact that these are meaningful features. For those of you that do machine learning, you know, does anybody do machine learning here? Yeah, of course. Okay, awesome. So you guys know that feature identification and selection, like this is the true art of what we do, right? And so the idea here is to draw insight from features that exist in the cognitive science literature to design the features and the structure of our models in a way that can support more efficient inference of these latent human mental states. So what we did was take Eugenio's features as the observations, and we designed a graphical model to infer the latent human mental state. And what we did was first design a low-level classifier that would automatically tag each utterance a person said in that conversation to its low-level dialogue act. And then we designed 2 graphical models, one which we trained on patterns of conversation that resulted in strong team consensus, and another that we trained on patterns in conversation that resulted in weak team consensus. And we trained these 2 models on the largest publicly available data meeting set. And that data meeting set, we were very grateful, for who knows what reason, they had actually, it was teams of 4 that came together to design a remote control. And then after each of those meetings, they actually had the participants write down individually what they thought they had agreed to in that meeting. So that actually provides us our ground truth. We can score the consistency of those 4 post-experiment summaries to determine whether that team left with strong or weak shared understanding. And so when we formalized the qualitative model into a model for which we can perform inference, what we were able to show for the first time is that Eugenio's qualitative model can actually be translated into a predictive statistical machine learning model for team consensus. And if you remember, so Eugenio said that the individual dialogue acts were probably not meaningful to delineating strong and weak consensus. But these higher level patterns were. And we see that in our results as well. So we really don't do much better than chance when we use the lower level dialogue acts. But when we use these meta labels or these features proposed by Eugenio, our ability to accurately delineate strong and weak consensus increases. Now it's 62% accuracy, so there's signal there. But the question is that good enough for an agent to actually be useful in our team meetings? Can an agent that can predict strong and weak consensus at 62% accuracy with a false positive rate of maybe about 30%, can that agent help us be better human teams? Or is this really not good enough? So we investigated that in a human subject experiment. I'll go into that next. Now, I will take a moment. Usually I go over it kind of quickly, but you raised sort of multimodal data. The data set that we trained on did include some forms of multimodal data, and we could look at synthesis of natural language conversation and some of these other signals. Interestingly, when we incorporated head nod, we didn't incorporate, so affect and emotion are a little harder, and they're not in the data set that we trained on, but we were able to look at the impact that head nod has. You think that should be important, right? Like if everybody's like nodding at each other, like maybe you're all more on the same page than if someone in that room is like shaking their head. And it turns out it does help just a little bit, but really just a little bit, and it wasn't a statistically significant improvement. So it's interesting. It seems like Eugenio's features, the patterns and information exchange really do dominate here. What we were also able to show was that the model is general in that you can train it on one team discussing one topic of conversation, and it's actually predictive to an entirely different team discussing an entirely different topic of conversation. So, because it's general patterns in how we exchange information. Like, this is incredible. And so what we did to test this model is we used it in an entirely different setting. We used it to develop an intelligent agent, an intelligent teaming agent, that would watch two people's conversation as they planned an emergency response deployment. And then if the agent felt that the team had sort of weak shared understanding with regard to some of those decision points, it would interject and say, team, why don't you revisit topics A and C? And so in this way, we can experimentally determine whether an intelligent agent can potentially enhance our ability to form team plans. And so we compared our system to an alternative interactive baseline. You can't compare to no system. That's a straw man case. That's not academically honest. You always, when you're evaluating an interactive system, you need to compare your interactive system to some other interactive system, because it might be the very fact that the system interacts at all that provides some benefit to the team. So we compared our system to an alternative interactive baseline, and what we found was that when our system asked the team to review topics it felt the team had weak consensus on, the team's post-experiment summaries increased in their level of consistency by 18%. Like, that is huge. That is like a huge percentage. And it's also a statistically significant result, not meaningful and statistically significant. Compared to the alternative interactive baseline, we didn't see any statistically significant improvement in the team's post-experiment, consistency of the team's post-experiment summaries. So like, wow. So like an intelligent agent that just watches your chat conversation and is like, hey, revisit that first thing you discussed. Like, you're gonna be a better team because of it. Like, how cool is that? Yep, go for it. Question?
Was that based on like what the people said after the meeting, or was that based on the machines return value?
The way this worked is it was a computer-mediated study, so it was two people interacting through text chat, developing their plan for a fairly complex planning problem. And then when they felt they had come to a good plan, the system would come in and say, please revisit topic A or topic B. And then the team could choose to further revisit that topic and maybe converge a little better. And then after the experiment, we had them write down what they believed they had agreed to.
Accurate there. What they wrote down was more accurate.
That's correct, yeah. Okay, so this is good, okay. But can a robot that just like listens to us and is like, you guys are all on the same page, like that's not like a super helpful teammate. Okay, so what we need is a little more. Like if the robot knows we're all on the same page, then ideally we also want the robot to figure out what it is that we agreed to. A robot that can listen to our conversation and figure out what we agreed to can infer its own role in the team, can infer the dependencies between what it has to do and what others have to do. And it can more intelligently adjust when it's actually going to execute, when things don't go according to plan. Okay, so what I've showed you so far is a little baby inference problem. Can we infer strong and weak consensus from team conversation? Just a binary decision task, strong or weak consensus. Now, what we want to infer here is like nasty. Like now we want to infer the commitments, the relationships, the ordering constraints. So I want to show you a short clip to illustrate how difficult human team planning conversation is. You guys don't realize it when you're in it, but when you watch a video, it makes it clear. Okay, so this is from one of our experiments. So the team was planning a deployment of robots and medic crews to 8 rooms. Some rooms had casualties that had to be rescued. Some rooms had environmental hazards that needed to be remediated. And the requirement was that robots had to inspect the rooms before the human crews entered. Simple enough. Okay.
I think we should plan to have as many people working at once as possible.
Divide the whole space and send a red robot to check room A to D, blue robot to check H to E.
Wait, but then we have one time step where A and H are being checked, and there is nothing for the other teams to do. Partition is good though. So how about...
Okay, you're right, but I just noticed we have people in problems in rooms B and G. So step 1, B, blue.
doing step 2 like that isn't good for the other crews, since there is only one mechanic and 2 meds.
Correction with robots. Step 2 would be F red and C blue, and step 3, hey, red robot got damaged.
Okay, we only have one robot now.
Send blue robot to...
Okay, so this goes on for a little while. So if I were to stop you there, I gave you the scenario, you listened to a snippet of conversation. I mean, somehow when people leave these meetings, they're relatively in consensus, but maybe you can kind of imagine why an agent that's helping you revisit points could be helpful. Can you guys figure out from that partial plan what it is they inferred? What it is, what their plan commitments were? You can? Go for it. What is it they committed to?
I thought you were asking. I didn't know it was a rhetorical question.
Oh, no. I have a lot of trouble inferring, what the commitments are from that, that plan snippet. Yet somehow we hold these meetings every day, and we're able to leave meetings, without thinking for hours what it is that we agreed to. So, why is it that we're able to do that, and why in this context is it so hard? So human conversation unfolds in cycles, and it's noisy. So anywhere between 15 and 80% of a conversation in our studies doesn't end up in the finally agreed upon plan. So you have a significant noise rejection problem. Even for this, what I would maybe generously call a moderately sized problem, the size of that latent plan space, like the number of possible plans, a system might have to search through to try to figure out the one that maximizes the likelihood of these observations, is on the order of trillions. This is really hard. So how is it that people do this? Well, so people highly leverage their information regarding the structure of the planning problem. We use that as a scaffolding in our meetings. We know what our goals are. We know who the players are. We know relatively who can do what. We know if there's some sequencing constraints. And through our conversation with each other, we're piecing our conversation together on this scaffolding to try to infer the finally agreed upon plan. So the question here is, can we enable the system to use this sort of structure? Can we design an inference technique that utilizes this structure that can enable this inference process to be almost as efficient for the machine as it is for a person? So what we did was design a graphical model. What this graphical model does is it takes in each utterance by utterance and each predicate, or sort of committed to action in that utterance, and it tries to stitch them together locally and then globally in a way that results in a global plan that maximizes the likelihood of the observation seen in that conversation. And as we're doing that process of stitching together things, we need to figure out, not just sort of fit everything in, but we also need to figure out what we throw out. Okay. And what we do is we incorporate the logical component through a plan validation step. So we take this graphical model, we perform inference on it using Gibbs sampling, and through that sampling process, what we do is we preferentially explore that sort of trillion-sized plan space. We move through it to explore it, and we preferentially move towards and sample from parts of that space that are more likely to result in a valid plan. So that improves the efficiency of our inference process. And we do that plan validation component using state-of-the-art techniques from the automated planning community. In particular, their plan validation tools. So computing whether a plan is valid is much, much faster than trying to generate a plan from scratch. We can sort of incorporate this in the inference process relatively efficiently. And so what we see is that when we incorporate information about the logical structure of the planning problem, that's this condition PDDL here. We incorporate that information using a planning domain description language, PDDL. We see we're able to reject 100% of the noise in the conversation and actually infer the finally agreed upon plan with a little over 90% accuracy, which is quite good. If we don't include any information about the structure of the planning problem, that's this no PDDL. And we do worse. We're only able to infer about 80% of the finally agreed upon plan. But interestingly, if we give the system the wrong goals or constants, that's like giving the system like the wrong plan. Like if I told you a completely different plan specification and then had you listen to that conversation, like you would be very confused. And it turns out the system is confused too. So if you give it basically the wrong planning problem, it does more poorly. And so that gives us an indication that this system is using the information about the structure of the planning problem in a way that fairly well corresponds to how people use it too. Okay, so far we've talked about inferring plan commitments at this like low level, like you do this, I'll go here, you do that, then I'll do this. But people don't always sort of discuss their plans at that low level, right? One of the things that people are really good at is coming up with these high-level strategies and communicating at the strategy level. So we've also looked at sort of this problem in the lab. How is it that we encode or represent people's high-level strategies for solving problems in a way that the robot can then use to elaborate? And so what we found is that in the vast majority of our experiments, people that, when we ask people to solve a problem and then write down how did they solve it, and they write down their high-level strategy, about 60% of those natural language specifications can be encoded in a formal language called linear temporal logic. This is amazing because linear temporal logic is a formal language that we can incorporate directly into many of the state-of-the-art automated planning solutions. And so by doing this, we can potentially develop sort of an AI human collaborative planning framework. So we conducted an experiment where we took humans' high-level strategies for solving very hard planning problems, and we formulated them as preferences within the optimization function of an automated planning technique. And what we saw was that by using human sort of intuition, their high-level strategies, the AI system was actually able to come up with better solutions to those problems than it could on its own. Meanwhile, this is kind of interesting because I'll just point this out. We did this study with MIT students who are arguably like world's experts in problem solving, right? And we conducted this study when we had our MIT problem-solving experts solve what are the IPC, the International Planning Competition problems. So these are the problems you give to the state-of-the-art automated planning techniques to see which planning technique is like the best in the world this year. So who do you think did better, like MIT students at solving the problems or the state-of-the-art AI automated planning techniques? Wait, so, so who says MIT students? Who says automated planning techniques? It was MIT students. So as far as we know, no one ever conducted a study in which people solved the IPC problems, and MIT students outperformed the automated planning techniques. Okay, so now would anybody outperform the automated planning techniques? That I don't know. We haven't conducted that study. But how cool is this? We could potentially take the intuition or the high-level strategy from an expert. Like, here's a strategy for solving this very hard problem. And then we can give that to an automated planner to then produce the fully elaborated plan and potentially leverage like the best of human capability and the best of AI computation. Okay, so what I've talked through so far is representations and inference of various human mental states for agents to infer human mental states and then use its inference of human mental state to augment human planning in some capacity or another. So far it's been pretty abstract, but so where can this be applied? I come from the aerospace department, so I have a special love and interest for aerospace applications, for time-critical, safety-critical applications. We're currently working on applying some of these techniques, as well as others, to help enable future concepts in which pilots fly with autonomous wingmen. So who's seen Top Gun? Okay, so for those of you who've seen Top Gun, you know, like Goose is the wingman. Imagine an F-35 pilot flying with an autonomous goose on a mission. Okay, like that's cool. Okay, that's like a big vision for the Air Force. But it turns out that actually flying the mission is one part of what you need to make a system be able to engage in this way. So the mission planning process is incredibly intensive. It's pilots getting together before the mission with whiteboards, discussing and deconflicting their plan at a very low level, ensuring that all the constraints and capabilities of the different aircraft are being considered. Is that something that that can be enhanced through an autonomous agent being integrated? Absolutely. But why is it potentially meaningful or useful for an intelligent agent to integrate in this process? An intelligent agent that has an understanding of the plan that was discussed, then flies that mission, can engage in the after-action review or the mission brief at the end of the mission. So that's where the pilots sit down and they review what happened and they discuss if anything didn't go according to plan and they discuss how they're going to do things differently or better in the future. If an autonomous system does not engage in that process, if your autonomous goose does not engage in that process with you, that's like your team member like not coming to practice. Like, why would you want to work with that system over time in a case where your life is at stake if you can't work with it to influence it and help it learn to work with you better and more safely? And so, you know, this is an incredibly exciting project for us. Okay. So what we've talked about so far is a system that's able to learn from listening to us, learn whether in consensus, what is it that we've agreed to, and potentially augment our team planning. But there are many things that go into teamwork that are not explicitly said. So just because we talk about how we're going to work together does not mean we're going to work effectively together. A medical student could be told for years, and I guess are, how to do the job of a medical student. I guess for 2 years. My husband was a medical student. He's a doctor. So you spend 2 years doing your book learning, and then you spend 2 years as an apprentice in the hospital. Do you walk in that first day despite being spent years, being trained to do that job and just know how to work in the team and how to be a good medical student? No, you don't. You really need to do more than just talk about how you're going to do your job. You need to be able to learn through apprenticeship and learn through observation. Okay, so if we take the example of the hospital floor, this is really not an easy thing to do. I mean, there's like a lot of variables. There's like a lot of considerations, and anybody coming into a new environment is gonna, sort of feel overloaded. But our machine learning techniques also feel overloaded. And so the question here is, how can we structure the observations from this environment in a way that allows the machine to learn with relatively few demonstrations, maybe like a dozen days in the hospital of shadowing someone making decisions, and is able to develop a predictive model or a policy for how that person will behave or act in the future. So to do this, we turn to well-established models of human decision-making. Now, unfortunately, unlike consensus and inferring commitments, there is no well-established cognitive model for how people solve multi-criteria decision-making problems. But we do know is that learning through comparisons is a foundation of this process. So people learn very, very effectively through comparisons, and especially paired comparisons. So this is commonly used to elicit people's preferences. I don't know if you've ever sort of done surveys, but someone might be, or even like eye tests, like is this better or is that better? Pairwise comparison. Is this better or is that better? This is a common way that designers will solicit preferences or priorities from human decision makers. But can you imagine your robot system following along the doctor in the hospital and being like, wait. Like in this situation, if this changed, would I do this or this? And it's going to ask you, I don't even know how many, hundreds of thousands of those questions, and that's how it's going to learn the workflow of your hospital. That's unreasonable. Typically, the systems do explicitly query the user, but why do they have to? So that's what we thought. Why do they have to explicitly query? Why can't they instead take observations of the expert decision maker and compute their own pairwise comparisons to infer these implicit priorities and preferences. So we developed an alternative policy representation where the system learns through comparisons, but those comparisons are computed implicitly from observation. And then those pairwise comparisons are then used to train ranking models. So what the system does is every time a nurse or a doctor makes a decision in that hospital, the system says, okay, you made the decision with this huge feature vector, this huge context vector. Now, what I'm going to do is infer that the decision you just made in this moment must have been equivalent to or better than any other decision you could have made at this moment. Okay, so you bootstrapped your data by 2n. In the next alternatively, the system can also say, any decision you did not make must have been equivalent to or worse than the decision you did make. So you get positive and negative examples, and you bootstrap your data. And then you use those transformed observations to train your learning model. Okay, how does this work? Well, this sort of learning through observation or learning through apprenticeship had never been successfully demonstrated for resource allocation and scheduling tasks. And so we were the first to be able to show that using this, this alternative policy representation, we can actually, with very few examples, learn strategies that emulate true experts. So this was the PhD work of a grad student of mine, Matthew Gambale. He recently defended, and he's actually now working at Lincoln Labs. He's going to start on the faculty at Georgia Tech next year. And so what he did was, in collaboration with Lincoln Labs, he took demonstrations of experts solving anti-ship missile defense problems. So how do you allocate, how do you protect a ship from like incoming threats? You need to sort of like send out decoys to distract, the incoming missile, or to directly hit it and neutralize it. And so Lincoln had a fairly large data set of people solving these problems across a large set of problems. I think it was over 100 or so. There were only 16 demonstrations in which an expert mitigated all threats. So these were perfect demonstrations. So we took these 16 perfect demonstrations and trained our learning model. Similarly, we worked with a local Boston hospital to collect data on the decisions made by a resource nurse on a labor and delivery floor. So the resource nurse is like an air traffic controller. Actually, she's doing a job that's known to be harder than that of an air traffic controller computationally. So she has somewhere around like 12 to 20 direct report nurses who she's assigning to different rooms, to different patients at different times. She's the keeper of the OR schedule. She's monitoring patient progress on all of those boards there. And this whiteboard summarizes the current status of all the patients and who's assigned to which patients on the labor floor. So we developed a high-fidelity simulation environment. We had a few dozen nurses and doctors come in and engage in that high-fidelity simulation environment and provide us demonstrations of the decisions they'd make throughout the day. And we use that data for training our pairwise ranking model. Okay, so how did it work? Well, on anti-ship missile defense, we trained that model on 16 expert demonstrations, and the learned model actually performed statistically significantly equivalently to the average domain expert. So you train on the best examples you have, and the system actually performs comparably to the average expert. Like that's with 16 demonstrations. And also interestingly, the learned scheduling policy did perform better than human demonstrators on more scenarios than vice versa. And that was a statistically significant result. Although in this case, there's really no rationale for why. I mean, you are training on perfect demonstrations, so maybe you're going to get a policy that's better than your average, but you're really only going to ever do as good as the quality of the demonstrations you receive from a human. So in that case, like the system's performance is really kind of upper bounded by the performance of a human. Okay, well, can we somehow intelligently develop a hybrid system, an AI-human collaborative system that can do better than either the AI system or the human alone? We can. So what we did was take the expert demonstrations on relatively small problems that a human could solve and use them as seeds and as bounds in branch and bound search to enable the AI system to solve much larger problems than it could have done on its own and much larger problems than a human could do on its own. So we could solve much larger problems than either can do on their own in just a few tens of seconds. Super cool. So this is a similar idea of taking like the human's experts strategies learned in one context and sort of transferring it and enabling the AI system to use human intuition, use human creativity, and be even better in a situation the AI couldn't have done on its own. Okay, so how about the hospital example? So the hospital was really interested in this project because there's no formal training for these resource nurses, these air traffic controller nurses. Their job is learned through apprenticeship over many, many years, and in some cases even decades. So there's no school they go to. There's no like handbook they have for how to do their job. So you can imagine the process of training someone new up and doing that job is very hard. And if we can automatically codify the knowledge that this person has, we can use that to train novice nurses. That's one application for this work. Another application is, the application that I'm very excited about, is a robot that can automatically learn the workflow of a labor floor, can more intelligently do its support work. So in hospitals around the country and in Boston, there are a number of service robots that are applied to deliver medicines, to deliver linens, to help turn over rooms. But they're generally, there's not many of them. You don't see them everywhere. Why don't you see them everywhere? Because in these complex settings, like they need to be explicitly told what to do. Okay, like they need to be explicitly tasked and scheduled. Who's tasking and scheduling them? Like this person who already has 20 like direct reports. Like that's crazy. And an air traffic controller, the span of control maybe goes from like 12 to 17. Like an air traffic controller can handle like somewhere in that number of aircraft. An aircraft manned by a human with all of human intelligence. Here, she's overseeing nurses that have all of human intelligence. And then you're going to give her like a fleet of robots that she has to task and schedule at the lowest level. Like there's many studies over about a decade, academic studies, for why these systems are not adopted. But it does not take a rocket scientist to figure it out. So a system that can automatically learn the workflow of the labor floor can instead suggest what it should do next. And it's a much lower burden for a person to just accept a suggestion than it is to think through and task and schedule. So we conducted experiments to see if our system could serve this purpose. We took the training data from the high-fidelity simulation environment, and we conducted controlled experiments in which the system in that simulation environment provided suggestions to the doctors and nurses. And we had those doctors and nurses accept or reject those suggestions. We then also fielded a robot on the live labor and delivery floor. And so what that robot did was actually use OCR and read that handwritten whiteboard to take a picture of the current status of the live labor and delivery floor and then make a real suggestion for what should be done next. So I'll show you videos of both. In this study, we evaluated both computer-based decision support, like an AI agent in your computer, and we evaluated embodied decision support, like a physical robot giving you suggestions. And if anybody's interested in that, I could talk about the differences between computer-based decision support and robotic decision support in Q&A. But I'll pause here. I'll show you the video and then talk about what we saw as the outcomes.
What is a good decision?
Right, like, and it kind of made me like, I don't know. Like, that's the What is a good decision?
I recommend placing new patients in triage bed number 5.
What is a bad decision?
A bad decision would be to place a scheduled cesarean section patient in group 13 and have Nurse Kristen take care of her.
Ginger, what's a good decision?
I recommend placing a scheduled section patient in group 10 and Nurse Meredith will take care of her.
I don't know if you played the back one. For me, it was the one.
Always playing so bad.
Ginger, what's a bad decision?
A bad decision would be to place a scheduled cesarean section patient in group 10 and have Nurse Meredith take care of her.
I agree.
Yeah, so interestingly to us, across both computer-based decision support and robot decision support, the nurses and doctors accepted the system's recommendation 90% of the time. This is quite good. So I think this is quite close to a system that can read or understand the workflow of a hospital floor and suggest, should I go and deliver this medication to this room at this time, the linens to turn over this room at this time. So what this means to me is that the days of thinking of robots as teammates that have to be explicitly commanded at the low level, like we're transitioning out of that. Like we're moving into a world where using new techniques, robots don't need to sit on the sidelines and wait to be told what to do, but they can learn our implicit priorities and preferences, and they can make suggestions, they can anticipate what we need, and then upon our approval, take actions without explicitly being told what to do. Okay, so towards wrapping up here, so I spend a lot of time today talking about inferring plans from discussion, trying to learn policies for behavior or decision making from observation. But if you think about a sports team, like you can talk through your game plan, and you can watch a lot of videos for how to play the game, but like you will not play that game well unless you train together. So my lab also has a significant amount of work looking at developing machine learning models and algorithms that enable robots to co-train with us, to train and practice using the standard techniques that pilots use to practice together, emergency response teams use to practice together, and actually sports teams as well. Okay, so back to our bigger goal. So to enable a robot teammate, that robot needs to know what we're thinking, it needs to know what we're going to do next, it needs to make quick adjustments when things don't go according to plan. So hopefully I've convinced you here today that we're getting towards robots that can sort of begin to infer what we're thinking, and robots that can anticipate what we're going to do next. Is that it? Is that like the end of what we need to make a great robot team member? No. So what are we missing? So far, we have a robot that can listen to the game plan, practice with us, learn from observation to figure out what actions it should take. But it's all one way so far, right? It's all the robot sitting there trying to figure out who we are, what we're going to do, and then do something intelligent. What we need sort of in the next sort of phase of work is more than that. So open challenges in this field are, we still, there's some really interesting early work, but still remains an open challenge. How do we enable a robot to learn how to influence us, for example, through communication? How can a robot learn how what it does or what it says will change the human's behavior in some way? If the robot thinks it has a better plan, then can it influence that team? And that's really an under-actuated system, right? Turns out one of the most ineffective team coordination behaviors is to start explicitly telling your partners what to do. That is the hallmark of a team that in every objective measure will not perform well. Humans are very effective at understanding these models and learning these models of how to implicitly influence others. Everything that we've done, and really most of the field has done, has been looking at teams of two and trying to understand how these dynamics scale or how the dynamics differ as we move to larger groups is a really interesting problem. What happens when you plan, you observe, you practice, and then something goes horribly wrong? You are so off plan, it's something you never discussed, it's something you never practiced. People are really good at accommodating, at dealing with these situations. In fact, in most human-machine systems, this is the role we really rely on people to serve. So how is it we enable a robot to work with a person in one of these really, really distinct or different situations? And then finally, how do we develop a robot that can transfer its knowledge over time and learn over time? And not just on its own, but it needs to be able to learn in a way that's compatible with how humans are learning. So if a person is training to do a task over time, they're going to get better and better at it. If a robot is using a machine learning model and algorithm, it's going to train on its data and get better and better over time. But one thing we know about human teamwork is that if people independently develop very high-quality strategies for doing a task, but those strategies are different, when you bring them together, that team performs worse than if the team had developed suboptimal strategies individually, but those suboptimal strategies were compatible. So in order for a robot to be able to learn over time, over weeks, over years, and generalize to vastly new situations the way a human does, it needs to somehow model this process in a human, right? And that's an open question as well. Okay, so that is the end of my talk. I can wrap up and take any questions. Go for it.
So sure you probably participated in times, but I probably watched a few too many sci-fi movies or read too many sci-fi novels, but the whole like teaching robots how to influence humans without humans knowing about it seems kind of sketchy to me.
So there is a field of work in deceptive robots, robots that are trying to plan to deceive their human partners. And I guess for anybody that runs human subject experiments, if there's going to be any deception in your protocol of your human participants, that needs to undergo special review. So I think your instinct is right on. In this case, I wouldn't, deception and influence are probably different things. So influence can be as something like, I'm going to reach for this. And what I'm going to infer is that because you see me in that space, you're going to work over there. And I know that if you work over there first, we're going to mesh our work more efficiently and finish the task faster. So by taking like a small change in my plan or taking some small action, I can sort of infer or predict how that will change my human partner's behavior. Communication is a type of action. So if you yell like, that building is on fire, then most people will run away. But maybe you want the system to be able to predict firefighters will run towards it and use that to its advantage if it sees a firefighter. I don't know. Like communication is a means of influencing the behavior of others. And we want to develop a system that can influence the behavior of others in a predictable way. Yeah? Yeah, go for it.
So in the hospital, in the hospital with the robot that suggested things, what was the orange one? How many? I know you said that there were 90% of suggestions were accepted, but how many of those accepted suggestions turned out well?
Ooh, that is an excellent question. So a really nice thing about the Lincoln Labs data set is that in that anti-ship missile defense problem, there's a score you get based on how you do in that game. And that provides us the ability to assess the quality of the system's suggestions. In the hospital, we really just have to go with the philosophy that the resource nurse is an expert and the decisions that they're going to make are the standard, the gold standard that we compare to. There's really no objective measure. And that's actually an issue for research and for development. Yep, go for it.
Is there any work towards explaining why the robot chose a certain course of action? Giving some kind of reason?
Excellent. So in the work I presented here, the system was never exposing explanations or rationale for the decisions that it was making. That's something we've worked on in the lab, not on these projects, but on the hospital project in particular. We trained a number of different machine learning models to understand how they would perform for a resource allocation and scheduling task. And fortunately for us, decision trees vastly outperformed neural nets, SVM, the whole other set of things we tried. And decision trees are an inherently more interpretable model. So future direction for us is to begin looking at a system that can sort of expose an explanation or rationale for the decisions that it's making. That's been shown to be a very important component to building trust and facilitating adoption of these systems. Yeah.
Adaptation offline. If you have like a considerable data set to look at how humans or how the nurses react to when there's a mistake or when there's a problem, have you considered, I guess, creating a plan for the robot based off of how nurses react off plan and
Yeah.
part of the plan?
Yeah, no, we don't have a data set like that. And so probably our and other labs' work in that direction will largely hinge on the ability to find the right domain to gather that sort of data set. And some of the problems with that is those situations are relatively less frequent. And so it's very hard to do something with that until you can study humans' response and have a data set to learn from. Yep. Oh, yep.
In the picture with the hospital resources manager and like the whiteboard, why didn't you just like write all the information on like Excel or spreadsheets or whatever?
Okay, so there's benefit to them for, it's a large team of people to have it visibly displayed and be able to be editable by anybody very quickly. So there's reasons it's a whiteboard, but fortunately the partner hospital we worked with is currently transitioning to a screen and online format in which all that data is also being captured electronically and updated. So that's the way of the future. There are human factors reasons why that whiteboard is not the worst idea, but it certainly poses challenges for a robot that needs to understand something about the state of the floor to make a decision.
It's a description after we're able to figure out what people are doing. Like, how does it know what people are doing when it's not just on the whiteboard?
So say that for me one more time.
You had mentioned earlier that like it's able to figure out like if it's in a workplace and it's able to go around and figure out what people are doing. Like, how does it get that description out there? It's pretty cool.
So for the system that we developed, its entire knowledge of the state of the floor is drawn from that whiteboard and then a few other small data sources that are in the computer on when rooms are changed over, when they're noted as ready for a new patient. So you are dependent on the data that you can readily collect in real time. But we felt it was really important to demonstrate that the system could take real data off a live labor floor, not just in a simulation environment. And a robot needs to work with the human space that it's put in. So it was an interesting robotics project to get the robot to read that whiteboard. It was kind of fun. Yeah, okay. Go for it.
Yep. So you looked at maybe transitioning that healthcare robot into more of like a triage role rather than just a bedding role. Like, would that be possible, and have you looked at it?
No, we haven't looked at it. We have not looked at it. A triage role. So I'm less familiar with it, but what I'm told is that ERs have sort of similar challenges to labor and delivery in sort of moving people through rooms and sort of unpredictable events. The nice thing about labor and delivery and why we started there is there's designated like process flows where in an emergency room, like when someone comes in labor, there's kind of like a tree of how things are going to progress, and you don't exactly know the time, but you know at some point either this is going to happen or that's going to happen. And then in an ER, it's a harder domain in that sense. Okay, thanks.